Hello, Longhorns. Today we're going to take a look at lesson number 8, coming out of chapter 5, pages 165 through 168. The topic of this discussion will be potential energy. Before we move to potential energy, let's revisit the last problem that we had in lesson number 7. For our kinetic energy chapter, we left off with this particular problem. We had a student that was wearing frictionless inline skates, and he was on a horizontal surface who had been pushed by another friend with a force of 45 newtons. How far must a student be pushed starting from rest so that her final kinetic energy is 352 joules? Now, on the last video, we had already acknowledged our force being 45 newtons. We also paid attention to the word rest. So it told us that your initial velocity was 0. Last but not least, they gave us our kinetic energy. The first thing that kind of comes to mind was KE, which is kinetic energy, equals 1/2 mv squared. But it made us pause because we also were talking about the work kinetic energy theorem. So the combination of this equation was W equals kinetic energy. Well, you learned a little bit before, what does work equal? And work can be replaced with force times distance. Well, we have the force and we have the kinetic energy. So what we did is we divided on both sides by F, and our equation turns out to be kinetic energy divided by force. This allows you to plug in your 352 divided by 45. And this brought me to my final calculation for this particular problem. Sometimes when you start working through a problem and you feel like you should expand it really, really far, I believe originally we had done force times distance was equal to 1/2 mv squared. The more I looked at the problem, the more I realized on setting up through the guess method, we would have ended up with two variables. D for distance, which was our unknown, so we knew we were correct there. But we didn't have the mass of the person. So that told me we had expanded way too far. I ended up bagging up and coming back to our simple kinetic equation that we already knew, and remembering that there was a work and kinetic energy connection because both of those were measured in joules. Now, today's topic, we're going to talk about potential energy. And if kinetic energy is the energy of motion, it's pretty basic and straightforward that this is the energy that is stored in an object. So when that object is at the very tip of the mountain and it wants to move but it's not, it has its highest amount of potential energy. Once you start moving, you now have kinetic energy. Potential energy simply means that it has been stored up and it can be used later for something more useful. The equation that we're going to use is PE equals mgh. So PE is your potential energy. We have the letter M for mass, which is measured in kilograms. G is for free fall acceleration, or simply put, gravity, 9.81. And then H for height. And we haven't really played with height since we left kinematic equations. So for potential energy, we have M times G times H. Now, let's work a simple problem. There are a couple of examples that are really straightforward when it comes to potential energy. Your stretch rubber band, it's 1. As long as we're holding it, the further you stretch, the more potential energy will build up. Another example we use will also be water going over the top of a waterfall. This has been a great energy creator for us as well, or a way for us to generate more energy. We've also learned that the yo-yo being held in your hand is a good example. And last but not least, the infamous bow and arrow. Now, the higher an object goes, the more potential energy it has. And this relates directly to your roller coaster project that you're working on now. So if you were asked, where does the roller coaster have the most potential energy? It's going to be at the very top of the highest hill. Well, where does it have the lowest amount of potential energy? It's going to be at the very bottom. Now, keep in mind that potential energy and kinetic energy have an opposite relationship. So if potential energy is high, kinetic energy will be low. Here's the question. Which object has more potential energy? The brick or the feather? Now, I'll give you a clue. The more mass you have, the more potential energy you possess. This probably was a good enough clue for you to say that our brick is our best answer. Here's another example. We're given a skyscraper, a chair, and a crane. The question of the day is, if I want to drop an apple from the top of one of these three things, where will be the most potential energy? Now, the higher the object, the more potential energy it can possess. And you're comparing your skyscraper, the chair, and the crane. Your answer, of course, would be your skyscraper. Now, let's try to see how this will work out if we're doing an equation. We're given a 50-kilogram shell is shot from a cannon on Earth's surface to a height of 425 meters. What is the gravitational potential energy of the system when the shell is at this height? Now, don't let the wording trick you. Take your time, find your given information, and as always, use your guess method. So let's try the guess method. My calculator is nice and handy. Now it's nice and handy. I have a 50-kilogram shell. It's going to be my mass. It's shot from a cannon at Earth's surface to a height of 425 meters. What is the gravitational potential energy of the system when the shell is at this height? So my unknown is potential energy. We just learned that our equation is potential energy equals mass times gravity times height. And remember, we're going to use our constant number of 9.81. Step number 5 is going to ask you, are there any substitutions? We have mass in kilograms, and we also have height in meters. These are our standard SI units for physics, so no substitutions are needed. I believe we are ready to solve. So I'm looking for potential energy. My mass was 50. The constant number that we use for gravity is 9.81. And they gave us a height of 425 meters. From here, we simply multiply. Be careful when you are entering your information into the calculator. This is also one of our second most common areas for mistakes to be made. We will be using scientific notation quite a bit in this unit and moving forward. So, my answer came out to be 208,462.5. And energy always has the unit of joules. Now let's say we're going to move this answer to scientific notation. It makes it a lot easier for someone to quickly glance at your paper and know if you're on the right track. This decimal needs to move to the left. So it means that my exponent will be positive. Let's move it. 1, 2, 3, 4, 5. My final answer is 2.08 times 10 to the 5th joule. We labeled our given information. We knew that we were looking for the potential energy that was created in this system. There were no conversions that had to be made. Plugging in your number using our constant 9.81 for gravity produced our final answer. Before we go, if you have any questions, be sure to send me an email because it's really easy for you to forget what those questions are before you happen to make it back to class. I'll also encourage you that on the page 168 or so, you're given additional practice problems. It's a good time for you to work through all 4 to 5 of those problems. If you get stuck anywhere, those are also good problems to bring to class on the next day. I've included example problems for you and a good flashback video, probably from the 60s or 70s, that goes to the topic perfectly. I'll see you guys in class.